We will have our second lecture today by Professor Sanjib Agarwalla. He's from Institute of Physics, Bhubaneswar. So Sanjib.
Yeah. So good evening, students. I can't share you because I can't see you because I have like zoomed in my slide, but I don't know whether you can see me, but I have so I have a request. Like, Professor Govinda Majumdar has made my life very simple because he has already introduced neutrinos to you in front of you, and he has mentioned many things, and you will see that there will be some overlap. But anyway, I will try to make my talk interesting to you. So I have one suggestion. When I just give talk and nobody is making any noise, it feels like, I'm in a haunted room. So I would request that if you have question, please stop me and I'll be happy to answer these questions. So let us spend next 1 hour rather than just, pouring in knowledge or information. Let's talk with each other. Okay. And we have a fantastic coordinator, Professor Satya. So if you have any question, raise your hand or stop me. I don't mind. I don't need to finish my talk. Okay. If we can talk with each other and clarify doubts and issues, that will be the purpose of this, 1 hour, we are spending in the evening today. So let's start the whole thing. I will just share some information about neutrinos and why neutrinos are very important and why we are spending this couple of hours discussing about these tiny particles. Okay, so I'm on my slide number 1. If my slide doesn't change, let me know. So in this slide, I will basically discuss how these particles, were introduced in the field of particle physics, these neutrinos, and Professor Majumdar has already discussed about that. So in 1914, there was a huge crisis or other problem scientists were facing. And what was the problem? So people were studying this two-body decay of neutron. Okay, at that time it was a two-body decay. That was the understanding we had. So a neutron, you can see in the left-hand side, a neutron is, this was our expectation that a neutron, if there is a sitting neutron, it can decay to a proton and which can also be at rest, you can assume, and you will have an electron. So since you have a charged particle, so I am assuming that you are familiar that electron is a charged particle. So if you have a charged particle coming out from a decay, then if you put some instrument, you can detect that charged particle very easily. Okay, so you can take like a homework problem. You can think after my talk that how we detect any charged particle. Okay, don't go to Wikipedia or any book or anything. Just think from your knowledge you have already that how you can detect a charged particle. Okay, so these electrons were emitting, and what people were doing, they were basically counting the number of electrons and their energy. Now, you think that if this neutron is sitting at rest, so it has a fixed energy, which is the rest mass energy. Suppose X amount of energy. And just Professor Majumdar told you that you measure the energy in the unit of MeV, GeV, or electron volt. Now, you are producing a proton which is also at rest. So it also has a fixed amount of energy. Now, if you subtract these two energies, see X and Y, then you should get a fixed amount of energy, and the outgoing electron, this electron should emit with that energy. So the expectation was that the energy of this electron will be monochromatic. Can you see my cursor? There, so the expectation was that whatever be the number of electrons, but they should come out with a one fixed energy. And you can see in this plot, I have just made a single line, and in the x-axis, you have the electron energy. But when we did the experiment, we saw that no, this is not correct. What we are seeing in the experiment is basically an energy spectrum. That means some electrons are coming with some energy, some electrons are coming with some different energy, Some electrons are coming with some different energy. And if you just plot it, you will see this distribution. Guys, can you see with this red line, the distribution? So this was the observation at that time. So you can see you have a crisis. You expect something and you see something. So this is what I am referring the problem that was hanging around 1915 or so. And in the right, you see two famous physicists. Already Professor Majumdar talked about Niels Bohr, and he is telling to Professor Pauli that, look, energy is not conserved in beta decay. So when you know about beta decay, I'm assuming, so beta particles are basically these electrons, okay? So he's telling, and I'm giving you a question. Can you just tell me what is they are looking at on the floor? This is just nothing but a spinning top, okay? So Bohr was telling Professor Pauli that energy is not conserved in beta decay. And that was a serious problem because, we know that in all physical process, apart from charge, energy and momentum is also conserved, right? We have not seen violation of these quantities in any physical process. Then in 1930, Professor Pauli, okay, he came up with a desperate remedy. So it was just, he came up with a suggestion, okay, that what if in this two-body decay, there is another particle, which we don't know, we have not seen it, but what if there is another particle, okay? In 1934, by the way, Fermi called that new particle as neutrino, okay? So Pauli didn't give the name neutrino. So he just assumed that, okay, what if we assume that there is another particle? You can see my cursor. So now it is no more a two-body decay. It is a three-body decay. And whatever the energy available, like the energy of the neutron, rest mass, and the rest mass energy of the proton, if you subtract, whatever energy you will get, it will be shared all the time between this electron that you see and this another guy, and it has to be chargeless. Now I am giving you another homework. You can try to find out why this extra guy has to be chargeless. Okay, try to understand after the talk. So he suggested that this guy should be chargeless, otherwise we could have seen it in our experiment. But it can share the energy with the electron, whatever is available there. And that's why sometimes electron is emitting with lower energy, sometimes it is emitting with higher energy. And that's why you see a spectrum of electron energy, not a fixed energy. So in this way, he was trying to explain the problem that we have in 1915. So he wrote, there is a neutral particle able to cross all detectors without leaving any trace and carrying all the missing energy. Okay. But I would like to tell you guys that he mentioned in his quote that I have done a terrible thing. I have postulated a particle that cannot be detected. So I want to emphasize on the word cannot be detected. That was the remark of Pauli in 1930. Okay. And he guessed that this particle doesn't carry any charge. So it will be really difficult, to observe this particle in a real experiment. But guys, we are very lucky that we have been able to detect these neutrinos. And that's why we are discussing about neutrinos today. Okay. So Pauli was wrong. And, we have detected neutrinos from various sources. And that will be the theme of my next 10 minutes, okay? So this was the problem, and the solution came through a particle called neutrino. And this is the way neutrino appeared into the landscape of particle physics. Okay, so let me proceed. So I am on my slide number 2. So if you look around, and if you are asking, okay, where from we see these neutrinos? So you can classify the sources of neutrinos in two categories. The one source is kind of natural sources, like, they are just coming from nature. And another is artificial sources, means you produce neutrinos in lab. Okay. So let us first discuss about natural sources. That means you don't have any control or handle on those neutrinos. They're just coming to you. Okay. So the first important candidate is the sun. Professor Majumdar already discussed about how neutrinos get emitted from sun. So these solar neutrinos. So why I say solar neutrinos? Because you are getting those neutrinos from sun. So in the daytime, if you just look at the sun, it is a point source, right? And you see that there is a sun. You feel that because you see the sunlight and the heat. But sun doesn't only radiate heat and light, but it also emits neutrino. Okay, there is a radiochemical, there is a process, there is a fusion process is happening inside the sun, which is the cause of behind this radiation of light and heat. But in that process, we also have neutrinos, and I will flash that reaction in front of you. So the summary is that sun not only shines in light, but it also shines in neutrino. And in 1960, we were able basically, to detect these solar neutrinos. And their energies are typically around MeV, okay? So if I am assuming you are familiar with electron volt, mega electron volt, okay? So their energies are around typically MeV range. Now, if you look at around your atmosphere, so I go to this candidate, you can see my cursor. So we have neutrinos from our Earth atmosphere. How? So when these cosmic ray particles, these primary cosmic ray particles, and what are they? They are basically protons. And when they interact with the air shower, they create some particles which are very short-lived particles. They create some particles called pions, kaons, okay? If you don't know about these particles, after the talk, you just Google and you can know some basic properties of those about these particles. So, but you have to take my words now that when this primary cosmic ray comes, which are basically protons, they interact with the air shower, and then they create some particles which are very short-lived and called pions or kaons, and they decay. They decay after some time because they are not stable. And when they decay, they produce neutrinos, okay? And these are called atmospheric neutrinos. And this pion decays to muon, and muon also is not a stable particle. It will also decay after some time. And you again get neutrinos, okay? So from the decay of pion and then the subsequent decay of muon, you get atmospheric neutrinos. So suppose you are sitting in Madurai, and if you build a detector, this is what we are planning under this Pottipuram Research Center, this project that we are talking to you. Our plan is to catch these atmospheric neutrinos. So wherever you are, if you just build a detector, so try to understand, we are not creating neutrinos. Neutrinos are there. They are passing through everywhere. But you are just trying to put a telescope to observe them. Okay, you think like that. So if you just build a detector in your backyard, or if you put your detector in backyard, they may not work because it will have too many noise, right? Because not only neutrinos, there are so many things are coming from cosmos. So if you need to go underground where the environment is silent, then you will be able to see these atmospheric neutrinos. But remember, you don't see neutrinos directly because they don't have charge. So when these neutrinos come and they interact with your detector, now you can ask me, what can be my detector? Anything. You think like a water, or you think like an iron, or you think like any scintillator, or you think like argon. So, your detector material can be anything, okay? But in all these materials, what you have, if you think carefully, whether you take an iron, whether you take a water, or whether you take a scintillator, you have ultimately neutron, proton, and electron. And we know that neutron protons are also not fundamental. You have quarks inside that. So what will happen? when neutrinos will come from any sources, they will interact with your detector particles. And what are these detector particles? These detector particles are just, I told you, neutron, proton, or electron. And there will be weak interaction among these neutrinos and these detector particles. And these neutrinos will produce their charge cousin. For instance, if you have an electron neutrino, you will see electron in your detector. So when I talked about sun, from sun, we have basically electron neutrino. And when I am talking about atmosphere, we have mainly muon neutrinos or antineutrinos, but we also have electron neutrinos or electron antineutrinos. But you don't need to go into those details, but just you take this message home that these neutrinos are coming to you anyway. They are not harming you anything, okay? When you put a telescope, you are just watching them, okay?
Hello.
Yes.
So can I ask a question?
Yes.
So how you distinguish that which neutrino is coming from sun or from other object?
Yes, very good question. What is your name, by the way?
Love Singh from Central University of Himachal Pradesh.
बहुत अच्छा question आपका. So let me explain. So when you look at sun, suppose you are in a daytime. अभी तो sun नहीं है, अंधेरा हो चुका है. So suppose you are at the daytime, go out and look at the sun. So I told you, sun is a point source, right? But if you look at your atmosphere, atmosphere is all around, right? चारों तरफ है तुम्हारे. Clear? So in your detector, I told you when neutrinos will come, you don't see neutrinos, but neutrinos will create their charge cousin. And you can assume roughly that this charge cousin will also move in the same direction of this neutrino. So the answer to your question, by seeing the direction of the outgoing particle, you can tell that, oh, okay, because if you are looking at solar neutrinos, they will come from one direction, okay? But if you are looking at atmospheric neutrinos, they will come from all possible directions. So you should make your detector in such a way that it can not only tell you that I have seen a charged particle, but it can tell you also the direction of that particle. So from directional measurement, you can distinguish that, no, this is atmospheric neutrino or this is solar neutrino. And another important difference is the energy. I told you that solar neutrinos are typically the energy in the MeV range, okay? But these atmospheric neutrinos, they have a wide range from few MeV to hundreds of GeV, okay? So when you see this final state particle, this charged particle, for solar neutrinos, they will not be that highly energetic. But when you create a particle in your detector from atmospheric neutrinos, they will also have very high energy. So the summary is, by looking at direction and by measuring the energy of the final state particle, you will be able to tell whether this is a solar neutrino or this is atmospheric neutrino. Is that clear to you?
Right, sir.
Should I proceed?
Yes, sir.
Good. So now these are the solar neutrinos and atmospheric neutrinos. And when people started detecting these particles, we saw something unexpected. And that unexpectedness basically gave birth to the phenomena of Neutrino oscillation that I will briefly talk about. But if you look at your Earth, okay, in your Earth, you have lots of neutrinos. Why? Because at the Earth core, you have heavy elements like, uranium, thorium, potassium, and you know that, they are not stable, they decay, right? Because the neutron over proton ratio is very large in these elements. So they are not stable and they will keep decaying till the neutron over proton ratio becomes smaller than 3.5, right? I assume you know this. So when this uranium, thorium, potassium, they will decay, which are there at the core of your Earth or in the mantle, then they are also emitting neutrinos. So if you build a detector underground or at the surface, you can expect that you will also see these neutrinos coming from the core of the earth or from the mantle of the earth. Okay, and these are called geoneutrinos. So I want to tell you that, why we're so much excited, because you see, these geoneutrinos were discovered in 2008. So I'm talking about a phenomena which was discovered just 12 years back. So we are not talking about a science which is like 200 years old. The neutrino science is developing. It is getting matured every day. And this is the time you guys can be the part of that thrilling journey, because we don't know many things about neutrinos. Okay, and you can be a part of this journey through this Pottipuram science project. Okay, so you have neutrinos from the earth, we have solar neutrinos, atmospheric neutrinos. Then in 1987 we have supernova explosion, and from that explosion we also saw some 20 odd supernova events, and these neutrino events are also in the MEV range. I want to tell you another fascinating source of neutrinos is the astrophysical neutrinos. So you see in the right hand side, I have written astrophysical accelerators. So there are high energy astrophysical neutrinos which are coming from the outer galaxies or even from very far reaching objects. Some reaction is happening there. And I want to tell you that we don't know exactly the mechanism of those reactions, but some reactions are happening there. And from that reactions, we are also having very high energy neutrinos. And till 2013, they were there only on pen and paper. We just discovered them in the year 2013 at the South Pole, where you have only ice. So you see the imagination of scientists. They went to South Pole and you have a huge chunk of ice there. What they did, they just dig the ice, they put the photomultiplier tubes, and they started looking at those high energy astrophysical neutrinos. And indeed, in last 7-8 years, we have seen more than 100 high energy astrophysical neutrinos. I want to reiterate again, we don't know exactly what are the sources of these neutrinos. We also don't know exactly what is the exact mechanism through which we get these neutrinos. So if you are interested, you can take this as your research topic. Okay. So we have detected these astrophysical neutrinos, but look at the energy range. I give you a homework problem. Please try to write down that 1 TeV is how much electron volt. Okay. And 1 TeV, this energy is how much larger than the typical energy of a solar neutrino. Just be curious, ask these questions. And also you try to understand what is the maximum energy we have achieved in CERN. Okay, few TeVs, right? So when we are detecting these astrophysical neutrinos, they are coming with energies which we will not be able to produce in our lab. That's why neutrinos are so interesting. You are probing a completely different energy scale with these guys, with these astrophysical neutrinos. Don't you think it is very fascinating that nature is telling you that, okay, I am sending these neutrinos. Why don't you catch them? Build a detector in your country, catch them. Okay. So these are astrophysical neutrinos. And try to remember, these neutrinos are traveling cosmic distances. So anything can happen with these neutrinos on the way. So if you build a detector and detect them, you are basically learning physics at a completely different energy scale and the distance scale. So this is really fascinating. And I'm telling you, we have just discovered astrophysical neutrinos just few years back. So the physics of astrophysical neutrinos is getting matured, and you have ample opportunity to, put your signature there and do research, do experiments, try to detect them. Okay. Then we have also the relic neutrinos, these Big Bang neutrinos. When, the universe was started, at that time, there are processes from that we have very low energy relic neutrinos. I'm not going into details, but I am just giving you a challenge that, so far we know that there are relic neutrinos. We have a cosmic neutrino background around us, but we have not been able to detect them. You can ask me why. Why, if you have so many neutrinos, these relic neutrinos, which were basically generated at the time of Big Bang, this is because we don't have a telescope which will be sensitive to such low energies. So you can also think, okay, can I build a telescope to look at these relic neutrinos? So this is a challenge. Now, if you look for this, apart from these natural sources, in last 50, 60 years, people have also created neutrinos in the lab. Just look at your room, okay? If you look at the light that you are having, okay? So do you know how you get the electricity? Now, in Tamil Nadu, you have lots of nuclear power plants, right? And the electricities are generated in those nuclear power plants. And what is happening in those nuclear power plants? Again, you have radioactive elements and they are decaying. They have a decay chain. And in that process, you see ample neutrinos, electron anti-neutrinos. And their energies are also MeV range. Okay. So you are getting these neutrinos for free from your nuclear reactors. And these are called these reactor anti-neutrinos. And Professor Majumdar told you that Frederick Rines and Cohen, they discovered these electron type neutrino using basically nuclear reactors in 1950. And then after 10-15 years, we also managed to create these neutrinos from accelerators. And there we use the same process with which nature produced atmospheric neutrinos. I told you just 10 minutes back that in atmosphere, we get neutrinos from the decay of pion and then subsequent muon. What people did, they replicated the same process in the lab around 1960s, and we got these neutrinos from accelerators. So these are called accelerator neutrinos. So we have accelerator neutrinos in Fermilab in Chicago, in Rutherford Lab, in CERN. Professor Majumdar talked about CERN. So CERN also has the capability to create these accelerating neutrinos, and in Japan, JPAR. So what I am telling you, while making a neutrino experiment in our country, we are not doing any crazy thing. All the countries that you can think of, even in Asia, in Europe, in US, all of them are engaged in neutrino science. They have built experiments to learn about neutrinos. Then why not our country should be also part of that? And Professor Majumdar told you that we are the first to detect atmospheric neutrinos. Then you can ask, don't need to ask, you should ask yourself, okay, why don't we have an experiment, neutrino experiment in our country now? And try to answer this, okay? And you will be convinced that we should have an experiment in our country. So let me proceed, okay? My job is just to convince you. I don't mind to cover all the slides. So this slide was already covered, that, when sun shines, we have also electron neutrinos. So you can understand, neutrinos are responsible for the life at the Earth. Can you imagine your life without sun? So if you talk to your parents, and if they will ask you what you are doing for last 2 hours, you should answer this question that, okay. So this is already familiar to you, that we have neutrinos also from sun, and these are solar neutrinos, and this is the chemical reaction, this is the fusion reaction. So in the sun, 4 protons get fused together, and then apart from light, you also have these electron neutrinos from the sun, because you need to conserve energy, momentum, and angular momentum. Okay. So you can say to anybody, if they ask you why you want to study neutrinos, you can say that without neutrinos, we will not be alive on the Earth. Okay. So this was also discussed. So Professor Ray Davies was the main person behind the detection of solar neutrinos, and Professor Koshiba-san, he played an important role while detecting the supernova neutrinos in the Kamioka experiment. And they were awarded the Nobel Prize in 2002. And I must say that when we able to detect these cosmic neutrinos, we basically opened a new window to the universe. We started talking to the sun. We started talking to the supernovae, which are very farthest distance objects, but we are talking to them through neutrinos, okay? And that was the beginning of the era of neutrino astronomy. Like, you know, just few years back, we discovered gravitational wave, and the era of gravitational wave astronomy just started a few years back. But around 2002, with the detection of solar and supernova neutrinos, the era of neutrino astronomy has begun. And this era, this field of neutrino astronomy is very fascinating. And there are lots of puzzling questions we have that we need to answer in coming days. So now let me talk about this atmospheric neutrinos. So I already discussed that how you get atmospheric neutrinos, right? From the decay of pion and the muon. But if you look at these reactions, then you see you have two muon type neutrinos and one electron type neutrinos. So when you plan an experiment, this is the plan of our project. We want to detect these atmospheric neutrinos. So if your detector can see muon as well as electron, then you expect that your muon neutrino flux should be twice of the electron neutrino flux, right? Because you have two muon type neutrinos and one electron type neutrinos. What else you can expect? Suppose you put your detector somewhere in your lab or underground anywhere. And I told you that your atmosphere is all around the earth, right? So these reactions are happening all around the earth and neutrinos are getting produced. And neutrinos, nobody can stop neutrinos. Nothing can stop neutrinos because its penetration length is very, very large. And I will give you an idea. So these neutrinos, if you have the upper atmosphere, neutrinos can directly come to you. You can see this picture, this cartoon. And if neutrinos are produced on the other side of the earth, since nobody can stop, nothing can stop neutrinos, those neutrinos can also penetrate the earth and come to you. And so these are called upward going neutrinos. And if neutrinos are coming from top, we call them downward going neutrinos. So since nothing can stop these neutrinos, if you put a detector somewhere on the earth, you will see neutrinos from all possible directions, right? So remember that. You expect atmospheric neutrinos from all possible directions, okay? And if you can see both muon and electron in your detector, then your muon neutrino number of events should be almost double the number of electron events, roughly, okay? This is the knowledge that we have from this slide, okay? I will not discuss this slide. Professor Majumdar told you that India was the first country to detect atmospheric neutrinos in polar goldfish. So let me just tell you that after photon, neutrinos are the second most abundant particle in the universe. And I just told you that we have huge amount of neutrinos as a cosmic bath, and we know them as a cosmic neutrino background. These were the neutrinos generated at the time of Big Bang, and they are there basically. So about 100 trillion neutrinos pass through our body every second. So I request you that please count the zeros over there. So neutrinos are omnipresent. They are coming from all possible sources in huge amount. What about sun? Sun produces 10 to the power 38 neutrinos per second, okay? So these are all stunning and very big numbers, okay? Now let me talk about neutrino interaction. So Professor Majumdar showed you a picture, right? With alpha ray, beta ray, gamma ray, right? Now, why neutrinos are invisible? Because they do not interact with light. So if anything will interact with light, then they have to participate in electromagnetic interaction. So just take my words that neutrinos are the particles. They don't take part in strong interaction. They don't take part in electromagnetic interaction. So they will not talk to light. They only participate in weak interaction. Please remember the word weak. And since they take part in weak interaction, when neutrinos will come and interact with your detector, and I told you that it will give you muons or electrons, they are charge cousin, this probability is very, very, very tiny because neutrinos only take part in weak interaction. And neutrinos can take part in gravitational interaction. So when you basically, these neutrinos come, they take part in weak interaction. And since they are only taking part weak interaction, and I told you the probability that a neutrino will come and interact with your detector particles, that probability is very tiny. You need huge number of neutrinos and huge number of target particles. Then the possibility that you will see some number of events will increase, right? The probability will be multiplied by the number of neutrinos and number of the particles that you have inside the detector. And that is why in our Pottipuram Research Center, this project that we are talking in front of you, we are planning to build a massive 50 kiloton iron detector. Now, I would like to request you guys that just try to imagine, I am giving you an homework. Please calculate that how many protons you have in 50 kiloton iron. A very simple homework. And try to understand that number. So such a big detector we need 50 kiloton. That means how many number of protons? Please calculate. And then if you have 10 to the power 40, 10 to the power 50, huge number of neutrinos, and if they will come and interact, you will see some handful number of events. Okay. So when we talk about alpha, beta, or gamma ray, the typical, stopping radiation in the lead is 50 centimeter. This is the mean free path of alpha, beta, gamma ray. But what is the mean free path of neutrinos? This is almost light years in lead. Lead is the heaviest metal. Okay. So in lead, neutrinos can travel a distance which is equivalent to light years without getting stopped. So you can understand, how different these particles are, how weakly they interact. And that is the challenge. That is the reason Pauli told that, guys, you will not be able to detect these particles. But human science has developed so much that now we have been able to detect these guys. Okay. So this slide you can just read. I am trying to give you same message that when the neutrino detection comes, it is a very hard experiment. You need to wait, should have patience, and you need to be big detectors so that you can see these guys. Okay, so just go through these slides. Now, this is the basic standard model of particle physics. This is a zoo of elementary particles. And in this zoo, you can see where are these three neutrinos. Okay, here you can see in the green color, you have electron neutrino, muon neutrino, and tau neutrino. So you have three different categories of neutrinos. And we tell them, we classify them in flavor basis. So we say, oh, you have an electron flavor, you have a muon flavor, and you have a tau flavor. I told you that they are neutral. And that is why it is very difficult to detect them. One of the reasons is this. And they are spin half particle. So I also want to give you some homework that suppose you are getting neutrinos from beta decay. Can you convince yourself that these neutrinos will have spin half but not spin one? Please try to put some pressure on your head after my discussion and try to figure out. And if you have any difficulty, get back to me. I have my email address in this on my first slide. Okay, so just try to convince that if a neutrino is produced from a beta decay, and I'm assuming all of you have heard about beta decay. why then this neutrino should have a spin half. So they are fermions, but not bosons. Clear, guys? Okay. And I told you they only couple to weak force. And now we know that neutrino oscillates. Professor Majumdar already told you. And something can oscillate if they have some mass, right? So since they have some mass, which we got to know very recently, so they can also take part in gravitational interaction. But that interaction is super tiny because the mass of the neutrino is very, very tiny, less than an electron volt. Okay. And the mass of the electron, I just told you, it's almost million times lighter than electron. Okay. And you can ask me the question, sir, why neutrinos are so different particle? Come on, they are 1,000 times smaller than electron mass. Why? What is the reason? And to be your surprise, we don't know. Really, we don't know that why neutrinos are million times lighter than electron. Because electron is also a fundamental particle. Neutrino is also a fundamental particle. Then why God gave so much mass to electron, but very tiny mass to neutrino? And this is an open billion-dollar question, guys. Okay. So you can also study about that. We really don't know that why neutrinos are so light. So this is an open question. We still don't know what is the reason. Okay. So when we detect neutrinos, I told you we don't see neutrinos directly. If an electron neutrino will come, you see this cartoon, you will see electron in the detector. If a muon neutrino will come, you will see a muon. And if a tau neutrino will come, you will see a tau. Now, electron, muon, and tau, they have different masses. Okay, and they are all fundamental particles. But electron is stable, and muon and tau, they are not stable. So they can decay, but they are all fundamental particles. Okay. So what the summary, the take-home message from this slide, you should not forget that you never see neutrinos directly. You see their charged cousin in this way. Okay. So you need to plan your detector, prepare your detector in such a way that you can see these electrons, muons, or even tau in your detector. Okay. So I will not go through this slide because Professor Majumdar already told you how we discovered electron, muon, and tau neutrino. But only one message. This tau neutrino, you think like it is so obvious, but it was just discovered in 2000. Okay. When I was doing my BSc basically. So when I was in Bachelor of Science, I was doing in my college, these tau neutrinos were discovered in Fermilab. Okay. It was postulated long back from the theory point of view, but it was first time, we detected them in 2000. So again, I want to tell you guys, we are talking about some science, some fascinating science, which is happening now. And you have a golden opportunity to be a part of it. Okay, here is another fascination. When first time I saw this Super Kamiokande detector, I can tell you guys, I felt like goosebumps. And that's why I always discuss this picture when I talk to you fresh guys like you. So this is a picture of a Super Kamiokande detector. You know why Super Kamiokande is so famous, right? You have seen, this detector has seen solar neutrinos, atmospheric neutrinos, and the Nobel Prize was given because of the detection of atmospheric neutrinos and for the discovery of Neutrino Oscillation in this detector, in this Super Kamiokande detector. So guys, can you see these small dots? Plenty of them, right? These are not dots. These are basically photomultiplier tubes. And you can see a person, couple of persons are fixing some photomultiplier tubes on a board. And this is a steel tank, which is filled by pure water. Okay. So this detector is located in Japan and almost 3,300 feet underground in the Mozumi mine. I had the good fortune to stare at this detector from close, and I can't forget that moment basically. So what is this detector? It consists of a cylindrical stainless steel tank you can see the diameter. It is pretty big, and it holds almost 50 kiloton liters of ultra pure water. Okay, so in water, what you have again electron, proton, and neutron. And when the solar or atmospheric neutrinos are coming, they are interacting and they are emitting electron or muons. And when these electron and muons, they passes through water, they emits Cherenkov radiation. Okay, and these photomultiplier tubes, they are the eyes, they are your telescope through which you see those Cherenkov radiation, and you can say, okay, I have seen a muon. That means a new mu has come. Okay, so this is a picture. I want to tell you guys, this is the way you see a muon or electron in this super Kamiokande detector. Okay, so in the left hand side, you see what are these dots. Again, these dots are basically your photomultiplier tubes. Okay, and what are these colors? Colors are basically the amount of energy, okay, that this photomultiplier tube has collected in terms of electronic charges. Okay, so when a muon passes through water, basically a Cherenkov ring is passing through your water, and if it is muon, then the ring will be very, very sharp. Can you see? The edge of this ring is very sharp. But if you have an electron ring, then it will be fuzzy. Can you see in the right hand side? Okay. I am assuming that you are all familiar with Cherenkov radiation, 1958 Nobel Prize. Just go do Google and search who was awarded. This is a homework problem, man. You just take a look who was awarded the Nobel Prize in 1958 and for what reason. Okay. The reason was that person discovered Cherenkov radiation. So what is Cherenkov radiation? This is basically an electromagnetic radiation, right? When a charged particle, moves through any dielectric medium, and if its speed is more than the phase velocity of light, then it will emit Cherenkov radiation. So you can ask me that can a particle move with a speed which is greater than the phase velocity of light? So, sir, are you violating special theory of relativity? I want answer from you. We are not violating special theory of relativity. So can you take home this question, that when you have a charged particle moving inside the water, take this example in Super Kamiokande, and they are emitting Cherenkov radiation, that means the speed of this charged particle inside this water medium is more than the phase velocity of light in that medium. How can it be? Are you violating special theory of relativity? Please put some stress, think about this. Okay. So you see, just looking at these ring patterns in Super Kamiokande, we can distinguish, okay, this is an electron neutrino, this is a muon neutrino. Okay. So what happened in last
Sanjib, another 10 minutes.
Years or so? Yes, Satya?
10 minutes, I said.
Yeah, fine. So here in this slide, you can see I have noted down some fantastic world-class experiments. I will not read the names. You can go through the slides. And from all these sources, we have detected neutrinos, and we have detected various types of neutrinos. You can see in the left. But one thing is common. When we have detected these neutrinos from various sources, and guys, just try to understand, when we have observed these neutrinos, they are coming from various sources. A sun is completely different from reactor, atmosphere, or accelerator. So these sources are completely different. The neutrinos which are coming to us, their energies are completely different. When they are coming to us, the distance they are traveling, that is also quite different. But one thing is common. When they are traveling from source to detector, they change their flavor when they move in space and time. And this is the phenomena we referred as neutrino oscillation. Okay. And this is a mass-induced phenomena because neutrinos should have mass, they have mass, and that's why there is a mechanism with which they can change flavor. So when a neutrino is emitted from CERN, it is emitted with a flavor electron. But on the way, there is a probability that that electron neutrino can change its flavor to neon neutrino. And this is what we are talking about, neutrino oscillation. So in our this Pottipuram Research Center project that we are all discussing, which will be happening close to your place, okay, in those detectors, we will see the oscillation of atmospheric neutrinos. In atmosphere, a new mu will be created or a new will be created, and they can oscillate to nu tau. And in our detector, we are not sensitive to tau. So they will be basically lost, and we will see less number of neon events. Okay. And this is the way we will also see neutrino oscillation in our detector. Isn't it very fascinating that, few miles away from your place, you are going to see this phenomena by your eyes? Okay. Just think and feel happy about that. Okay. So one small concept, when we say massless neutrinos, so why we say that neutrino oscillation is something beyond the standard model of particle physics. So I showed you the standard model of particle physics, a cartoon, right? So the basic theory of standard model, which I don't have time to go and discuss, it predicts that neutrinos are massless. Because to give a mass to a particle, you need to have both a left-handed guy and a right-handed guy. Now you can ask me, what is left-handed, what is right-handed? So in this nomenclature, in this language, you see when the momentum direction of the particle is opposite to the spin direction of that particle, then we call that guy left-handed. And if the direction of the momentum and the spin are aligned in the same direction, we call them right-handed guy. So this helicity is nothing but is the projection of spin onto the direction of momentum. So in nature, we have only observed left-handed neutrinos. There are no trace of right-handed neutrinos. And in nature, we have seen right-handed antineutrinos, but there are no right-handed neutrinos. Okay. So that's why, since you don't have both-handed particles, you can't write a mass term for neutrinos in the basic standard model of particle physics. So here I'm just writing a simple mass term. This psi is like the wave or the associated with the particle that you are thinking of, okay, or a field basically. So you need both left-handed field and right-handed field to write down the mass term. But I told you that we have not observed right-handed neutrino. We have only seen left-handed neutrino. So we are not allowed to write down a mass term for neutrino. But I just told you that in neutrino experiments, we have seen that neutrinos are oscillating. Now, if something is oscillating, then it should have mass and they should mix with each other. This is the concept of neutrino oscillation. So again, you can see that neutrinos are not following the traditional path. Theory is telling they are massless, and data is telling that they should have mass. So you see the conflict, and that's why I can proudly say that this non-zero neutrino mass that you require, you need to explain this oscillation phenomena is the first experimental proof for physics beyond the standard model. Whatever picture we have about the standard model of particle physics is not complete. And we need to accommodate neutrino mass and mixing in that picture. We need to work hard. So guys, isn't it enough as far as motivation is concerned that we understand this theory and we understand how can we accommodate neutrino mass and mixing in the standard model picture? Again, this is a billion-dollar question. And I can assure you, if we build experiment in training This experiment will play an important role to shed light on these issues. Okay, I don't have that time to go into details, but you take my words, and if you are willing, I can discuss in detail offline. But this experiment will able to shed important light on this direction, on this fundamental question that is unresolved now. Okay, that is a mystery to us. And this INO experiment, this detector that we are planning to build, it will not cause any harm to anybody. It is just going to improve our knowledge about our universe, our knowledge about these neutrinos. Okay, so I don't want to discuss this slide. This is the famous slide, the 2015 Nobel Prize. So I also want to give you homework. Can you guys count after this talk how many Nobel Prizes were awarded in the field of neutrino physics? If any one of you can find that number and how and when, please write to me. Okay, I'll be very happy. I'll feel happy that I have penetrated someone's mind. Okay, so please think or Google or explore the literature and tell me how many neutrino Nobel Prizes have been awarded to this neutrino science, okay, in last 15, 60 or 100 years or so. Okay, so 2015 Nobel Prize was received by these two gentlemen because they solved the long-standing solar neutrino anomaly and atmospheric neutrino anomaly, and both the anomalies require that neutrinos should oscillate. Okay, I don't have time, but I just want to tell you that neutrino oscillation is not a black box. It is just a very simple phenomena, and you have all encountered that in your life. Professor Majumdar has already elaborated that. I'm sure if you have physics background, you have done the double slit experiment and you have encountered the interference phenomena over there. So, you know, in quantum mechanics, sometimes you can treat a particle as a particle, or sometimes you can treat as a wave, right? And this is called the wave-particle duality. So that's why if you think that these neutrinos are basically wave, and you can go back and forth between particle nature and the wave nature, then the mass of that particle will determine the frequency of the oscillation of that wave. I told you that neutrino oscillates. So if something is oscillating, then you need to determine its frequency, right? And who will determine that frequency? The mass of that particle. So you see in this cartoon, if you have a wave number 1 with this frequency, and you have wave number 2 with this frequency, and if they interfere, you see this pattern, right? This is just the simple interference phenomena. If you get opportunity tomorrow, lockdown is over, go outside tomorrow and throw a stone onto the pond, and you will see this kind of ripples, right? And try to understand, are you seeing any interference phenomena there? Okay, so that same phenomena is responsible behind this flavor change of neutrinos from one flavor to another when you allow them to travel. Okay, so when you want to write down this theory of neutrino oscillation, these mixing angles. So in the left hand side, you have these neutrino flavor eigenstates. I tell you electron neutrino, muon neutrino. So when you detect neutrino or produce neutrinos, they are in the flavor basis. We call them electron or muon neutrino or tau neutrino. But when they propagate, then you can't identify them as flavors. They propagate in mass basis, which are this nu1 and nu2 or nu-i and nu-j. And you can connect these two bases with just a simple 2x2 rotation matrix. This is an unitary matrix. And this matrix can be parameterized with the help of this mixing angle. That means a flavor neutrino is a linear superposition of mass neutrinos. And this superposition is determined by this mixing angle. So when we plan these experiments, we want to measure that frequency of the oscillation. And this is this parameter. It tells you the frequency of the oscillation. And this is the theta, the mixing angle. So this theta And this delta m square, okay, this is just, they are just fundamental parameters. And I want to convince you guys that these parameters are as fundamental as the mass of an electron. Have you ever asked that why we measured the mass of an electron? I don't think so. We were taught in the class that we have an electron and its mass is 0.5 MeV. But somebody did experiment to measure that mass. This is a fundamental parameter. So that's why we also need to measure the frequency of neutrino oscillation and also the mixing angle with which they mix. And they are also that fundamental like electron mass. So it is our duty to build new experiments and to measure these parameters. And I can assure you that if we can build with your help this neutrino detector close to your hometown, we will be able to measure these parameters more accurately. I am not telling that we will be the first to measure this. People have measured that, but our experiment will also measure it and will also give us some new information. So I don't want to go into detail. This is my summary slide. I'm sorry, Satya, I'm taking 1 minute more.
Yeah, sure. No.
So far, I was just talking over last 1 hour about these neutrinos, but I want to convince you that this project, if it happens close to your hometown, this will be a basic science project. And our whole intention is to learn about our universe. Okay. And I think as a humankind, as a mankind, this is the most important question we should try to answer, that how our universe looks like. Why do we exist? Okay. Why we have only matter? Like, you know that there are antimatters also, right? There are antiparticles. But if there would have been antiparticles in nature, then this matter antiparticle, they will fuse and will be vanished. So why we have only matter? Why we have only electron, proton, neutron, but we don't have positron, or we don't have antiproton or antineutron? We need to produce them in lab. But why they are not there in nature? Who created this imbalance? Why our universe is dominated by matter, but there is no antimatter? And I can tell you, these neutrino experiments will be able to answer some important questions along this direction. That why do we exist? Again, I want to wrap up my talk that if you do an experiment dealing with neutrinos, it will tell you, man, why you exist. So you are most welcome to join us, be a part of this fascinating journey, and let's try to understand neutrinos with this Pottipuram research project that people are bringing to your place. Be a part of it and enjoy. So I'm happy to take any question if you have now.
Thanks, Sanjib. Can you unshare your screen?
Unshare.
Yeah.
Stop video.
Okay. So you can you see the chat? There is a question.
That is how can I see the chat? Okay.
Okay. Otherwise, I'll read for you. It says, sir, is there any criteria for choosing the location to place the detectors, or we can get the same results regardless of the location we choose?
Very good question. I want to know the name of this student.
His name is Ayyadurai Muthu.
Oh, great. You have just touched the nerve, basically. So you are asking why we need to go to Theni to do this experiment. So first of all, I need to tell you that why we need to go a place where you don't have other activities, like you need a shielding. That shielding you can obtain if you go underground or if you dig the belly of a mountain. So you need some coverage of a rock. Why? Because I told you, we are planning to observe neutrinos, atmospheric neutrinos. But from atmosphere, we have a huge number of cosmic muons also, right? They are directly coming to your detector. And these neutrinos are also coming. And these neutrinos will also give you muon. Now, how can you tell that, okay, I am not seeing a cosmic muon, but I am seeing a muon from a neutrino? So you have to stop these cosmic muons before they enter into your detector. So you need some shielding. So you need to go underground or you need to dig the belly of a mountain. And that is what we are doing. We are planning to do at your place, that we will dig a tunnel without harming anything around, and it will be a safe tunnel, and we will dig the belly of the mountain and we will put our detector there. Now, next come to the question, why only Theni? Why can't we do it in Bhubaneswar? So you need to make sure that you are digging a rock, and that rock has to be stable, right? When you are digging that rock to make a cavern, it should not fall down. So you need to have a good quality rock, and it has to be stable. Another thing is the climate. You see why the rock has to be stable also? Because it is 50 kiloton iron. You need to understand that place has to sustain a 50 kiloton massive object. So that rock has to be very solid. Okay. And another thing, the climate, the atmosphere. Okay. So depending on all these criteria, that your rock has to be stable, because this experiment will run for next 50 years. And generation after generation in Madurai, in Theni, in Tamil Nadu, they will be able to do science with this experiment. Okay. So you need the stability. So all these factors are responsible, and we have done a very careful study, a very careful survey. If somebody tells you that we just choose this location randomly, this is wrong. This is wrong. And if you need clarification, you are most welcome to contact any of us, and we can tell you what steps we have gone through before we decided to go to your place and do the experiment in Theni. So these are the factors that comes into the picture when you want to fix a location of the neutrino experiment. I have not told you the full story, but lack of time, but this is just a small summary.
We will
appreciate your question.
Further also tomorrow, day after tomorrow.
Yes.
Okay. Any further questions? Yeah. Okay. So the participant says, we understood. Thank you very much. Another question. Is electron neutrino emerge from sun continues as electron neutrino, or interconvert among themselves as electron to muon and to tau? I think you have answered this.
So I can repeat, Satya, for 1 minute.
Yeah.
So look, when neutrinos are produced inside the sun, I told you I showed you the reaction. So take a look, guys. Just take a look at this reaction. It is a very easy reaction. So when 4 protons get fused together, you have these neutrinos in the final state along with light and other radiation. So this is kind of beta decay, right? So you have electron neutrino when you produce them at the place of the production. But as soon as they start traveling, whether in matter, whether inside the sun or just outside the sun, you always have a probability that this nu E can get converted to another flavor. And this will keep on happening. Nu will go to nu mu will go to nu E. As long as you don't disturb them, this phenomena will keep happening. The moment they will come into your detector and they will interact, this phenomena will be stopped. And that time you need to calculate that what is the probability if I start with a nu mu, I will get a nu mu. If I start with a nu E, I will get a nu mu in your detector. Does it answer your question?
Yeah.
Hello, sir. I have a question beyond the content of your talk. What is the difference between the 3 mixing angles, theta 1, 2, theta 2, 3, and theta 1, 3?
Very good question. Very, very good question. So I told you, okay. Very nice. So Satya, my slides are shared, right?
Yeah. Yes.
Yeah. So can you see, I forgot to ask your name. What is your name?
Love Singh, sir, again.
Okay, good. So आप देख रहे हैं यहाँ पर in the left side you have these 3 different flavors of neutrino, because we know that we have 3 light active neutrinos, 3 different flavors, nu E, nu mu, and nu tau. Now I told you when you produce them or detect them, you call them like in flavor neutrinos. But when they propagate in mass basis. And this is the mass basis, nu1, nu2, nu3. Now you see, you need to connect this, mass basis to flavor basis with this 3 cross 3 unitary matrix. Now, to write a 3 cross 3 unitary matrix, the most easiest parameterization you can think of in this way, right? It will have 3 mixing angles. It is just like you have studied 3 Euler rotations, right? You give rotation around x-axis, then y, and then z-axis, right? And you have x prime, y prime, and z prime. Now, what is the difference between 3 mixing angles? If I am talking about theta 1, 2, okay, so it will tell you that how much nu e and nu mu should be mixed to form a nu1 mass eigenstate. Okay. Similarly, if you talk about this theta 2, 3 mixing angle, which has a fixed value in nature, it will tell you that how much amount of nu mu and nu tau you need to mix to get a nu 2 mass eigenstate or nu 3 mass eigenstate. Okay. So these mixing angles will tell you how much these flavor neutrinos are getting mixed to give you mass eigenstates. Does that answer your question?
Yes, sir. Right, sir.
Good.
Okay. We have to close. Actually, it is 8:36 now. Actually, there's one question about, suggesting good elementary kind of, papers or books for further reading about basics of neutrino and about this project.
Yes.
We continue tomorrow and day after. So I'm sure, please just, keep this question in mind. We can answer it tomorrow. But Sanjib, I would like to take at least one.
Hello.
From YouTube, which is try to kind of be very short answer. Has the Pauli exclusion principle been observed in neutrinos? That is one question. And from the same participant, where do the most energetic neutrinos in the universe come from? And what gives them this enormous energy?
Yes.
Things are partially covered, but if you can just a little bit summarize quickly.
Yeah. So I think, the person who is asking this question, he has the curiosity. So I leave this question up to you, that when I say, these fermions, the neutrinos are fermions, right? I told you that they have spin-half particles. So now you should answer this question, that what would happen to Pauli's exclusion principle if you apply to these fermions. So I'm giving the connection, but you explore the connection. Okay. I'm just telling you that neutrinos are fundamental particles and they are spin-half particles. They are fermions. So will they obey Pauli's exclusion principle? You find out that answer. Okay. That will make you to learn something. And second, I told you about high energy astrophysical neutrinos, and they are of so much high energy. So we have some idea that, some reactions, very high energy energetic reactions are happening even the outside, at the extreme end of our galaxy or even outer galaxy. There are objects called GRB, gamma ray burst, or AGNs, active galactic nuclei. These are just some examples. And there, some very high energetic processes are happening. For an example, if a proton can interact with a photon, it's called P gamma reaction. Okay, that will produce some pions, very energetic pions, and that will decay like in atmosphere, and you will get very energetic neutrinos. But this is just one possibility. So I told you that exact mechanism of the generation behind this, or production mechanism of these high energy neutrinos, is not known. And you can take up this project basically and contribute if you can learn and tell us what is the process that is happening there. It is an open question.
Yeah, I think, Sanjib, there are more questions coming up, but nevertheless, I think we should stop because.
Can you just tell them if they have questions, they can email me?
Yeah, of course, you can announce, and you want me to place your email here?
Yeah, so guys, I feel bad that I'm not answering your question. That is my job to answer your question. So look at this email address. Okay. Tomorrow I'll be traveling, but I assure you I will answer your question. Just drop me an email. Okay, this is sanjib@iopb.res.in. From today night, I will be traveling till tomorrow night. But believe me, I will answer your question. Just drop your email. Drop an email with your query. Okay.
Yeah, I also placed the email on the chat box.
Yeah, and you can connect with our Twitter page to learn more about neutrinos.
Okay, thanks, Sanjib. We must close for today.
Thanks a lot, Satya, for doing this fab job. I would like to thank Professor Indu, Professor Murthy Saab, Datar Saab. I saw them. I want to just tell you 1 second, Satya. These students, 2005, I attended a school. That was my first school for neutrinos, and we were taught neutrino physics by Professor Datar Saab. Okay, who is still with us after 21 odd years. So you see the stamina, you see the encouragement that is given to us by him. And this is our job to pass that motivation or encouragement to you guys. Okay, so thanks a lot, and be excited about neutrinos.